okay? Um, so on Monday, we are left at this location. I'm not going to solve any problems in here. I'm just going to basically express how can we mathematically express the symmetry of, um, of a quantum mechanical problem. For example, we would like to find the electronic energy levels of the methane molecule, let's say, and the molecule has a symmetry group. Benzene, for example, is another one. I mean, there are lots of molecules with some symmetries. And so this is it's basically a subgroup of this rotational group O3. And basically the molecule is invariant under these rotations within the symmetry group, okay? So the question is, how can I express the symmetry condition in terms of the Hamiltonian, where, I mean, I need to use the Hamiltonian operator to solve for the energy eigenfunctions. What does it imply for the Hamiltonian, right? We were talking about this. And then I have said this, basically, there is this transformation from any wave function. If I rotate this wave function by a certain rotation by r, we obtain a rotated wave function, which is basically, we call this as this rotation operator applied on the old wave function. And then when I'm describing this, I actually use some kind of contour plus or whatever. And then I have said that this rotated wave function basically can be expressed in terms of the other wave function by this expression. Okay. And then I have shown that, well, dr is unitary. It's a unitary map on the vector space of the possible wave functions of this physical system. So it's actually called a Hilbert space, but I don't want to go into these kind of things. So basically the wave functions can be considered as some kind of vectors in an infinite dimensional vector space. It's actually an Hilbert space with an inner product defined on it. With this structure, this is actually unitary, meaning that, well, it is norm preserving. So I mean, if the wave function is normalized, the rotated wave function is also normalized. You can understand it like this, or you can understand it like that. We can also talk about this Hermitian conjugate of this operator. So the product of the Hermitian conjugate with the operator is equal to identity. Okay, so that's the identity operator, which is the same thing as basically the product in the opposite order. Or we can just say that the whatever, dr dagger is equal to the inverse of dr. Let me say etc. in here. I have shown this, so let me show that this is unitary. Sorry, this is a representation. Sorry. D from the group to, let's say it like this, operators on this Hilbert space of whatever, the space of square integrable wave functions on whatever, on that vector space. So it's basically gives us an operator in that space is a representation of the group. Of G. It's actually a representation of the group O3. We're not talking about the symmetries at this point. So I'm going to write down the symmetry condition later, all right? This is a representation of the group G. Why? Well, I'm just going to do it like this. So I'll just consider two successive operations. So let me say it like this. I have some kind of a wave function in here. So this is the wave function of my particle, let's say. First, I rotate by r. So let me call it like r. So I obtain some kind of a rotated wave function the first rotated wave function. And then after that, I apply another rotation. So that's, let me show it a little bit bigger in here. So that's S, in which case, this is the origin, let's say. I'm rotating around the origin. So in that case, I just obtain, well, it's the same contour plot, but it's rotated, all right? So that's psi double prime, okay? So in any case, so as a result, the composite rotation is this. It's the blue one in here. All right, this is the rotation by SR, basically. And I would like to see if my relationship is satisfied, all right? Let me say it like this. So first, I pass from psi to psi prime by this rotation operator, dr applied on psi. And from psi prime to psi double prime, because I'm basically rotating this one in here with S, so this is obtained by applying ds on psi prime, which means I'm actually applying the product ds multiplied with dr applied on psi, right? And the question is whether this psi double prime is actually equal to the rotation by, I mean, if would I obtain the same wave function if I just applied the SR rotation to psi, right? Something like that, okay? So let me check this, right? So I know this, right? This is psi double prime of R. Sorry about this. I'm going to write this relationship in here, okay? So this is, I know that this is psi prime of S inverse of R. So this S inverse of R is the argument in here, okay? I also know that psi prime of R is equal to psi of R inverse of R. Right here, I'm writing this relationship, right? Okay, so what I do is this. I just call this thing with some certain name. Let's call this as A, for example. I don't know. And I'm just going to write this formula in terms of A. So I know that psi double prime of R is equal to psi prime of A. But I know that the psi prime of A is given by this formula. So that's psi of R minus 1 applied on A. But now I write the value of A in here. So therefore, this is psi of, R minus 1 of S minus 1 of A. R. But I also know that this is the product of two inverses. It's actually the inverse of the SR products. Okay. So yes, indeed. So therefore, the second wave function is basically can be written in terms of the first wave function as this expression, which then shows that this statement is true. So therefore, this psi double prime is therefore is the rotation operator SR applied on psi. Okay, which also is this thing. So that's basically ds multiplied with dr. And finally, since this expression is valid for any kind of a wave function, we then conclude this. So that's basically the rotation operator corresponding to the rotation SR can be expressed as the product of these two rotations. So that's the end of the proof. Yes, that D thing is actually a representation. If you remember, we have defined the representation like that. This is a homeomorphism. Sorry. Do we call this as homomorphism? Yeah, I forgot the thing actually.
Yeah, we are calling them as homomorphism.
Yeah, all right, so it's not homeomorphism, right?
No, it's not. Yeah, it is something different.
right? So we have some kind of a group operation, and then on this operator side, there's these rotation operators also follow the same multiplication table. So therefore, this is a representation. It's a unitary representation, therefore. There was one last thing that I mentioned in there. There's the symmetric condition. Sorry about this. So how do we express the fact that this this molecule has this symmetric group by using these operators? Okay, let me actually, yeah, these are the trivial ones, so as a result, let's just forget about them. So the next thing is this. So I'm just going to consider this, for example, I think I'm going to do this calculation. So suppose that I multiply, this V of R is the potential energy function. Okay, so I have some kind of an expression like this, for example, psi of R, and there's actually some kind of a term like that, minus h bar squared over 2m Laplacian squared, right? I would like to solve this equation, for example. So that's the Hamiltonian applied on psi, all right? Let me just concentrate on this one, okay? So this V of R multiplied with a wave function, it gives me some kind of some other function, all right? I don't know if this is a square integrable function or not. Let's assume that it is, right? Basically, by applying this operator to one possible wave function, I obtain some kind of a wave function-like function, actually, right? So basically, this is another vector, right? This is an operator applied on a vector gives me another vector. Can think of it like this. Now, what I do is I just apply dr to that expression in here. I'm applying dr to v applied on psi, right? Let's think of it like this. And so that's the same thing as dr being applied on f. And this is an operator. So, well, let me say it like this. This is an operator applied to a function, just as seen in here. So I'm considering the value of that function at the location R, right? So when you do this analysis in here, this is basically V applied on psi evaluated at R minus 1R. So that's F R minus 1R. Okay. So therefore, this is V of R minus 1R with psi R minus 1R. That's equal to F R minus 1R. So this implies that probably I didn't need to do any calculation in here, but let's do it like that, all right? So I think I'm going to do one more thing in here. I know that this is a rotation operator applied on psi evaluated at R. So this is V of R minus 1R. Yeah, I didn't think this through, actually. First, let me think about this, right? Because I would like to make my point to be clear. Yeah, I think I'm going to do it like that, right? This is dr applied on f, evaluated at R. So what I would like to do is I would like to apply the inverse of this operator to this side, to both sides, actually. So as a result, on the right-hand side, I'm going to get f of R. Um, yeah, I actually lost the point in here. Sorry about this. Sorry, let me undo all of this. Let me go back to the beginning. Sorry about that. Probably I should have thought about this beforehand. I would like to obtain some kind of an expression in here. But in any case, we would like to solve this equation, all right? This is epsilon psi. Okay. The symmetric condition is this. You can express it like this, symmetric condition. But the symmetric condition can also be expressed in a different way too. Right? So it says that for any R, for any rotation in the symmetric group, okay, if psi is an energy eigenfunction of H with eigenvalue epsilon, let me write, with, let's say, eigenvalue, that's eigenvalue, let me shorten it like this, epsilon. If psi is an energy eigenfunction, then the rotated wave function too is an energy eigenfunction of H with the same eigenvalue. Right? That's basically the statement. Okay. So as a result, it's not saying that if I rotate an energy eigenfunction, I get the same wave function. No, it doesn't say this. It says that if I rotate this energy eigenfunction by a symmetry rotation, by a rotation in the symmetry group of the molecule, then you get another function, which is also an eigenfunction. It doesn't tell us whether this another function is the same as the original function or different. It can be anything, right? So let's just state it like this. So I'm just going to write down the same statement in terms of the mathematics. So it basically says that if H applied on psi is equal to epsilon psi, then it says that the H applied on dr psi is equal to epsilon dr psi. Okay. But how can I understand this? What I need to do is basically rewrite this equation in a different form. I basically write this equation in a form like this. I just apply the inverse of dr to that equation from left. Okay, so this is dr dagger dr. But since this is unitary, this is 1. And so therefore, I get this equation that, so therefore this dr dagger hdr applied on psi is equal to epsilon psi. Okay. So that's my, therefore, symmetry condition. I'm going to write this thing down again, right? Symmetry condition says that if H applied on psi is equal to epsilon psi, then this particular strange operator, right, dr inverse H dr, this particular operator applied on psi is equal to epsilon psi. Okay, I can express the symmetric condition mathematically like that. Now you can see that, well, this can only happen if this operator is exactly the same as this operator, because we're talking about like two operators with the same set of eigenvalues and same set of eigenvectors. These two operators cannot be different from each other. And so as a result, this is basically the symmetry condition now. Symmetry condition, sorry about this. Symmetry condition. Okay. Let's say it like this. This is for any rotation in the symmetry group. We should have this, that dr dagger H dr is equal to H.
John, this
Yes.
really reminds me the Schur's lemmas. Um,
Yeah, I'm
yani,
going to pass to that. So I'm going to
oh,
explain
really?
this as a
Okay.
commutative relationship, right?
Oh, okay, thanks.
But this is the starting point. So whenever we say that Hamiltonian has a symmetry, this is actually what we need, right? There's some kind of a symmetry operator. Um, if the Hamiltonian we make a similarity transformation on the Hamiltonian by the symmetry operator, we should get the same thing, right? So you can check that. First of all, check that this thing, basically, I mean, let's say this equation is identical with the potential function being invariant under rotations. Under rotations, if the potential energy function is invariant, then the Hamiltonian is also invariant. Okay, so somehow the Laplacian part also satisfies that property, but I'm not going to show this. That's a little bit tricky thing. I don't want to confuse you, but it's basically, I have talked about this thing before. So under rotations, the Laplacian doesn't change. Under any rotations, actually. But for a given potential energy profile, there are some certain rotations where this potential energy profile doesn't change under some rotations. So these are the symmetry operations. Okay, so note this, right? I can actually think of it like this. Note, we can rotate Hamiltonian operator sorry about this. We can rotate or transform Hamiltonian operator by, so let me say it like this. From the Hamiltonian, I'm going to pass to a rotated Hamiltonian, and it's basically rotated by R, right? So the rotation of the Hamiltonian operator is basically the rotation of any operator. You can rotate an operator by multiplying the operator from right and from left by this rotation operator, but this has to be in the form of a similarity transformation, okay? Let's say it like this, okay? So this is true for any R, any R. So we say that, right, a rotation R is in the symmetric group G, symmetric group of the molecule, G, sorry about this, G, if and only if the rotated Hamiltonian is the same thing as the original Hamiltonian, right? So if and only if the Hamiltonian doesn't change under rotations. Or let me say it like this. If and only if Hamiltonian does not change under rotation R. Okay, so rotation is just a particular kind of symmetric transformation. There are other kinds of symmetric transformations, like, for example, charge conjugation, where you basically change the sign of the charge for every particle, right? This is one of the fundamental symmetry operations that particle physicists do, actually. So there's a gauge transformation, for example. In each case, we can express the Hamiltonian by some kind of a we can transform the Hamiltonian by some kind of a similarity transformation like that. Usually, if the transformation is not a symmetry of the system, the Hamiltonian will change under this thing, right? So if you rotate the Hamiltonian, it will change because the potential energy will change under rotation. But for some rotations, it won't. the Hamiltonian will remain the same, in which case we say that those rotations are symmetry operations, and they belong to the symmetry group, okay? So you can actually think of it like this, right? So basically say that the symmetry group is basically the group of operations that leave the Hamiltonian invariant, right? So as a result, the reason why we call symmetry in here is that, I mean, if you just remember the original definition of symmetry, it is some kind of a geometric object, for example. After some transformation, there are some certain transformations that leave the shape of the geometric object invariant, right? So in physics, we actually use it in the same meaning, but instead of a geometric object, we talk about the Hamiltonian, right? So any transformation that leaves the Hamiltonian invariant is a symmetry. So it's basically the dynamics of the thing. So somehow the Hamiltonian describes the dynamics of the physical systems. So let's say it like this. Let me use these words only, dynamics does not, if the dynamics does not change under rotation. Okay. Because somehow Hamiltonian is this essential operator that gives us how things change with time, right? And by dynamics, we essentially mean this, okay? So that's also the case for in the classical mechanics as well. That's also the case in quantum mechanics, whatever. I'm not going to look at these time-dependent problems in here, but this is essentially what it is, okay? So in any case, right? So that's the symmetric condition. By multiplying this equation from left by d, I can express it in a different way. So let's say it like this. All right, this is d dagger Hamiltonian d. So that's the symmetric condition, right? Sorry. That's the symmetric condition. So what I do is I just multiply both equations by d from the left. Okay. In that case, we get identity in here. So our equation basically reduces to this. Hamiltonian multiplied with dr is the same thing as dr multiplied with Hamiltonian. Okay. This is the commutation relationship, basically. Or I can basically express it like that. Hamiltonian commutator with the rotation operator is equal to 0. So that's the symmetric condition again. It's another way of writing the symmetric condition. Okay. Right. This is the point where the Schur's lemma is going to be very useful, because think of it like this. If this is an irreducible representation, then this condition will imply that the Hamiltonian has some, all of the eigenvalues of the Hamiltonian are degenerate, right? If this is irreducible, then it means that the Hamiltonian is just a multiple of identity. And so therefore all of the eigenvalues are the same. But of course it isn't, because this is a representation on an infinite dimensional vector space. So therefore it is reducible. So it actually contains many different representations usually. It's not just the, yeah, whatever. So we have to do some kind of a reduction in there, right? So we have to decompose this representation in terms of the irreducible representations. After that, this is going to be used. After that, we are going to apply Schur's lemma, and then we will state about these other things, actually. Okay. So one other thing in here is the one implication, right? First implication. Since we have said this, let me state this because I can sometimes forget. So this is something people call as Ehrenfest theorem. I don't know if you have seen this or not, but I'm basically talking about the expectation values of observables at different times. So for this, we just take the expectation value of the observable with a time-dependent wave function. And the time dependence of this thing is governed by this Schrodinger equation. It's the time derivative of psi is equal to h psi and so on. Okay, I don't want to go into this. So basically, the RMFS theorem says that the time derivative of that expectation value at time t is given by the expectation value of I over h bar, the commutator of the operator with the Hamiltonian. Okay, so that's the RMFS theorem. Right, let me show it like that, right? That's the statement of the RMFS theorem. There's also a version where if the operator explicitly depends on time, there's an additional term in here, but that's not something that we need. Okay, we have a commutator in here. We have also a commutator. So that's the first use. It's the first implication. So if R is a symmetry of the system, then the expectation value of this rotation operator is a conserved quantity. Okay, we usually do not use it like this, but in any case, this is one thing that you can actually state. So that's one first implication of symmetry. It implies conservation laws. So that's the first implication of symmetry. Okay. There's the symmetry of parity and things like that, in quantum mechanics, we actually use it, some of the symmetries in that form. But if the symmetric group is a Lie group, in that case, we usually express this conservation law in a different form, right? It's not in that form, but in a slightly different form. If I have time, I can also talk about this, all right? But I'm not going to talk about it like that, right? So basically, there is this relationship between the symmetry and the conserved quantities. So that's one version of the, in a way, Noether's theorem. The Noether's theorem is actually basically about the Lie groups, but it appears that for discrete groups as well in quantum mechanics, we can always talk about a conservation law. So Noether's theorem says essentially that if there is a symmetry, then there's an associated conservation law. A symmetry then there is an associated conservation law. Conservation law. There is something which is conserved. Okay, that's basically what it says. So it is this connection in here. What's the relationship? Well, it's basically this. This is my symmetric condition that the Hamiltonian is invariant under rotations. This implies that it's just a chain of mathematical relationships. It implies that the Hamiltonian commutes with the rotation operator. If the Hamiltonian is invariant under rotations, it implies that Hamiltonian commutes with the rotation operator. We just obtain some kind of a mathematical relationship. This implies that because of the RMFS theorem, the time derivative of this expectation value of the rotation operator is constant. So therefore, this is a conserved quantity, right? So as a result, the Noether's theorem is very simple in quantum mechanics. If there's symmetry, it is very easy to show that the expectation value of the corresponding representation of the symmetry, the symmetry operator is conserved, okay? So that's the first implication. There is this, the other implication. So the second implication is that, of course, there are these degeneracies of the energy levels. I'm going to talk about this, but not right now. Okay, so as a result, I'm just going to leave the dominion of quantum mechanics at this point. I'm just going to look at the classical problems, right? But let's remember that in quantum mechanics, I can express the symmetry, the fact that a physical system has a symmetry as the commutation relationship between the Hamiltonian and this representation matrices. Okay, so then we talk about the classical mechanics. Right. I'll be basically talking about the vibrational problems in small oscillation approximation. So this is important. I need to make a small oscillation approximation because in that case, the theory is basically a linear theory. I mean, we actually make this approximation to do this, to simplify the problem, to make the theory linear, in which case we can solve the problem exactly. Otherwise, the problem is kind of complicated. So like the pendulum problem in here, for example, think of it like this. So this is the pendulum thing. So that's m, this is the length, this is angle theta and whatever. So the equation of motion is this. Mass times L squared. This is the torque that's equal to minus mg sine theta, right? I mean, this is the equation in here. This is nonlinear. So this is nonlinear. What we do is we just make this approximation that this the right-hand side sine theta is proportional to theta. And so as a result, we just write down the equation of motion like that. Okay, so this is the linear approximation. So this is the small oscillation approximation. Can we use group theory for nonlinear problems? Not so easily, all right? So it's not that powerful for nonlinear problems. For linear problems, however, everything is perfect, so we can actually formulate this very easily, right? So as a result, I'm just going to make the, I'm just going to assume that we are always in this linear domain. So whether it is a pendulum or I don't know, the oscillations of the bonds in the methane molecule, for example, there are these vibrational things in here as well. I'm going to assume this small amplitude oscillation, so therefore everything is linear. Then there are these problems like this where I have talked about this problem before. I'm going to solve it again. But this time I'm going to use the machinery of the let me do it like this, machinery of the group theory. Okay, so this is a problem. This is a one-dimensional problem, right? We don't have any oscillations along that direction, so they just oscillate along this horizontal direction, all right? Just keep this in mind. So perhaps I could have thought about them as blocks. I don't know. In any case, the masses are the same, and these two spring constants are the same. So that's the reason why we have a symmetry. We have a left-right symmetry in here. Left-right reflection symmetry, basically. So the symmetry group is, let's say it like this. The group is basically contains the identity. Yeah, let me write it down like that, right? It contains some identity and some kind of I don't know, R is a reflection across mid-plane or something like that, okay? In any case, so in that case, this G is isomorphic to the cyclic group C2. So, oh, it is a symmetry group. What's the implication of the symmetry in here? Well, how can we use the symmetry property in this particular case in solving this problem? I'm just going to, I mean, how the group theory enters into the mathematics. How do we obtain the representations in here? In here, what we do is this. So I'm just going to draw this picture again, but this time in a slightly different way. So there's some kind of an equilibrium position of these two masses, right? There are these two equilibrium positions. So I'm going to call the displacement from this equilibrium position by x1, right, and x2. So they don't have to be equal to each other. So as a result, what we say is that x1, x2 is, well, right, are the positions, okay? So basically, this is a system where the degree of freedom is 2. Meaning that there are two positions, two independent positions, which you can determine arbitrarily. So there are no constraints between these two positions, right? That's what I'm saying. Okay, and then there will be two velocities and whatever. In any case, we then talk about this. I'm going to write this as a matrix form. So I'm just going to think about a matrix, a 2x1 matrix that contains both of these positions. So X is therefore is a vector that expresses the position of system, okay? So I'm not going to put a vector sign on top. I could have, but that's not necessary in here. So X in here is basically an element of this vector space R2. So this is actually configuration space. This is what people call. It's not the phase space, it's the configuration space, okay? Why did I do this? Sorry about that. So this is an element of that two-dimensional vector space, okay? So the thing in here is sorry, we're basically talking about this symmetry operation in here, which is basically the reflection. So how can we express the reflection in here? So basic idea in here is this. So let's say it like this. Reflection R corresponds to a transformation of this vector in here, okay? So this vector then under reflection is going to change. How does it going to change? So I think I'm going to do it like this. I'm going to make a copy of that picture. All right, copied. Now I'm going to paste, right? And then, all right, I flatten the whatever. So what happens is this. So there's this midpoint in somewhere in here. So the reflection is basically the switching of left with right. So what happens is that if I take, for example, this location in here, this dotted curve is basically converted into that dotted curve in here under reflection. So this position is then converted into that position. So I'm using this yellow things to basically express the location of the objects, the masses, after the reflection, okay? So as a result, this one will go here, and this one will go somewhere in here, right? Where these arrows, I mean, this arrow has a length like that, and this arrow has a length like this. So this arrow and that arrow has the same length, right? I think you understand what I mean, okay? So this corresponds to a transformation from x1, x2 to x1 prime, x2 prime, okay? So it's a transformation from x to some new coordinates, x prime. So these are basically the transformed coordinates. How do we express this? Well, for example, in here, so if x2 is positive, then after the transformation, the coordinate of the first particle, let's call this as x1 prime, is the coordinate of the first particle. First particle is this. Coordinate of the first particle is negative, so it is minus x2. And x2 prime is therefore equal to, right, it's the coordinate of the second particle is basically this one with a negative sign. Okay, I don't know if you have understood this, but this is an important thing. I'm basically writing.
I'm sorry, may I ask something?
Yes.
In the reflection operation, we are reflecting everything, right? Together with the system, not coordinate system. Point masses, everything.
No. All right. Reflecting the coordinate system, this is a passive transformation, right?
That's correct.
It's the passive point of view. I said that I'm not going to use it. Okay.
Okay, I see.
So whenever I say transform, I'm transforming the whole physical system.
Okay. Thank you.
Yeah. Everything meaning that the edges of the walls and things like that as well. So the earth also is reflected as well. Okay. So this is transformed into a new vector x prime, where the individual coordinates are equal to minus x2 minus x1. Okay, but you can easily see that this is basically this matrix applied on x1, x2. Okay, so this is my representation matrix. So let me call this as dr. I'm not going to put a hat in here, but it is basically the reflection operation that I do on the physical system, its effect on the positions. Okay. So therefore, let's say it like this. D is a transformation from the symmetry group from this one to 2 by 2 matrices. All right. So identity is represented by identity. So that's the case. And the reflection is represented by 0, minus 1, minus 1, 0. Okay. So that's our representation. We know how to decompose this. We know how to decompose this in terms of the representations of the symmetric group. So that part is known, but since I'm not going to use the representations, the irreducible representations in here, I'm not going to do this. So this is basically is to show you how these representation of the symmetric group appears. Well, basically, a symmetry operation is a symmetry is a transformation of the coordinates, and so that, well, it's basically this, right? This symmetry operation is a transformation from x to x prime, which is obtained from x by some kind of a linear map. And these are the representation matrices. All right, so these are the representation matrices. Now, there's the next question. So we know the representation matrices, but we have this idea of the symmetry of this original problem, right? Let me paste this again, right? This is our original problem. No, this is not the original problem, sorry. So that was the original problem. I mean, we would like to compute, for example, the normal mode frequencies for that problem. It is easy to see what the symmetry in here is. What does symmetry imply? So basically that this picture doesn't change under the symmetry operations. How can I express this symmetry condition mathematically? Okay. And the answer is this. So that's the symmetry condition. There are two different ways that I can describe the dynamics. One is the Lagrangian formalism, where we basically write down some kind of an expression that's called the Lagrangian. This is a function of the positions and velocities, right? You know what this thing is. So it's basically kinetic energy minus potential energy, if you remember. And then we write down the equations of motion by using the Lagrangian. And there's a Hamiltonian formalism. In quantum mechanics, we actually use the Hamiltonian formalism a lot. We never use the Lagrangian formalism, but in classical mechanics, we can use both of them. They are equivalent in a way. So Hamiltonian, however, is a function of the positions and momenta. So there's a slight problem in here. So I know how coordinates transform under symmetries, but I don't know how momenta transform. I can find no problem with this. It's a very simple calculation, basically. But this makes the Hamiltonian description of the symmetries a little bit difficult. So as a result, I'm not going to follow this approach, but I'll follow the Lagrangian approach because I know how positions transform. Therefore, by just taking a dot product only, I know how the velocities transform, right? I just need to take the dot product in here. So x prime dot is basically dr applied on x dot, right? It's the same rotation, same representation matrix applied on the velocity vector. As a result, to keep things simple, I'm going to follow the Lagrangian approach. So the symmetry condition says that the Lagrangian doesn't change under rotations. The Lagrangian is invariant. This is the same thing as saying that the dynamics is invariant under symmetry operations. But in any case, we will express whatever. I'm going to talk about this later. By the way, all of this are mentioned in some of the previous lecture notes that I have prepared. All of them are in these lecture notes. Probably there are some previous videos about this thing as well, right? So you may want to look at them without my mentioning to you on next Monday. Okay? I mean, that's the approach that I'm going to follow. Okay, let me stop here and then ask if you have any questions.